Hi everyone and welcome. In today's video, we're going to learn about the fundamental theorem of calculus. Now the fundamental theorem of calculus is broken up into two statements. There's two parts to it. In this video, we're going to take a look at part 2. If you're wondering what happened to part 1, don't worry, we're going to take a look at part 1 in the next video. I want to begin with part 2 because it's going to nicely answer some unanswered questions that we have about the connection between the definite and indefinite integral and wrap things up nicely. And so to that end, let's get started. Here is the statement of the fundamental theorem of calculus, part 2. This is also called like the evaluation part. Let's suppose that you have a continuous function on some interval. Let's call it lowercase f. If you can find an antiderivative of this lowercase f, let's call it capital F, that is, capital F differentiates into lowercase f, then it turns out that the value of the definite integral from a to b f of x dx, which represents the signed area under the curve f of x dx, is going to be equal to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So this theorem is very, very powerful because previously we have been computing the value of definite integrals, but we're doing so as a limit of Riemann sums. And that is pretty tedious and sometimes pretty difficult depending on what type of function is involved. So the fundamental theorem of calculus part 2 is saying that you can compute a definite integral by using antiderivatives, indefinite integrals. And it's like a two-step process. You first need to find an antiderivative. And how do we find an antiderivative? You have to compute the indefinite integral of f of x dx to get this general family of antiderivatives. And then you can evaluate the definite integral from a to b f of x dx as capital F of b minus capital F of a. So just subtract the antiderivative output at the upper limit minus the lower limit. And we use some notation to compactly represent this difference. So this kind of notation just stands for f of b minus f of a. And another thing I want to bring your attention to is that you can pick any antiderivative. You just need one antiderivative of lowercase f. So when you find the entire family of antiderivatives, you can pick any constant, right? And most often we'll just pick c is equal to 0. If you were to pick c is equal to 1 or c equals to 2, and you do this sort of difference, well then like the plus c and the plus c here will sort of cancel out because the minus sign will distribute here and it'll become minus c and they'll cancel out. So that's why it doesn't really matter which antiderivative you pick. You're going to get the same result either way. Let's begin by taking a look at our first example. We're asked to find the area under the graph g of x over the closed interval from 1 to 3. So the goal of this problem is to compute the definite integral from 1 to 3 of g of x dx. Now previously we would have to set this up as a limit of Riemann sums. And we did this with functions like x and like x squared, and things were getting a little bit complicated. So you can only imagine how difficult it's going to get with sort of these exponents. But the good news is that we're not going to be doing that now. We have the fundamental theorem of calculus to our advantage. So all we need to do is find an antiderivative of this function, just any antiderivative, and evaluate that antiderivative at the endpoints. Subtract the value at the endpoints, and we will have our answer. So to that end, first we're going to take the indefinite integral of g of x. We can just go ahead and apply the integral to each piece separately. To find the antiderivative of each piece, we can use the power rule. So add 1 to the exponents and then divide by those new exponents. So we get x to the 1 over 4 divided by 1 over 4. And for this other term, we get the new exponent as 8/3, and we have to divide by 8/3. And now you can simplify this because dividing by a fraction is the same thing as multiplying by the reciprocal. And you'll get 4 times x to the 1 over 4 plus 9 over 8 times x to the 8 over 3 plus the constant of integration. And now we can go ahead and evaluate the value of the definite integral from 1 to 3 of g of x dx as just taking any particular antiderivative. In this case, I'm just going to set c equal to 0 because I can take any antiderivative. And I want to evaluate this antiderivative from 1 to 3. So this means we have to take 3 and plug it into this function. That is represented by this expression. And then minus, we need to plug in 1 into this function, and that is this expression. Now you can use your calculator to evaluate this number, and you'll get like 26.325 minus 5.125. Subtract those two, you get 21.2. And you see how simple it was to compute? We didn't have to do any limits of Riemann sums anymore. We just had to compute an antiderivative, and then we had to evaluate the antiderivative at the upper limit minus the lower limit. And so now if we think about that question again, about the connection between definite integrals and indefinite integrals. We discussed before that they're very different objects. One is just a number, whereas the indefinite integral is a family of functions. But the fundamental theorem of calculus is relating them. It's saying that in order to find the value of the definite integral, we just need to take the antiderivative of f of x dx and then just evaluate that from a to b. And so this equation sort of relates the definite integral and the indefinite integral. And so there we go. Now we've answered that unanswered question. This is the connection. The indefinite integral helps us evaluate the definite integral. Let's take a look at this next example. We need to compute the definite integral from 0 to pi of sine of x dx. Now, trying to do this using a limit of Riemann sums is going to be very, very difficult because you're going to have like limits of trigonometric functions. So yeah, good luck with that. But guess what? We don't need to do that. To evaluate this, we can use the fundamental theorem of calculus and just find an antiderivative of sine. An antiderivative of sine is going to be negative cosine. And now we just evaluate this at the limits of integration and then subtract the outputs. So we plug in pi. So we have negative cosine of pi. Then minus, we got to plug 0 into here. So we have minus cosine of 0. Now cosine of pi is negative 1. The negative 1 with the negative 1 here becomes positive 1. And then over here, cosine of 0 is 1. With the negative 1, it becomes negative 1. There's also another negative, so it becomes plus 1. 1 plus 1 is 2. So what we've done here is we found the signed area under the sine graph from 0 to pi. Basically, we found the area of this hump. It happens to be positive 2. Now let's take a look at a slightly related signed area. It's going to be the signed area from 0 to pi under the graph sine of x dx. So once again, an antiderivative of sine is negative cosine. We evaluate the antiderivative at the limits of integration. So we take negative cosine at the upper limit, which is 2 pi, minus the value of the antiderivative at the lower limit, which is going to be negative cosine of 0. And this time we actually get negative 1 plus 1, which is equal to 0. So the value of this definite integral is 0. That is, the signed area is 0. And this makes sense if you look at the diagram again, because now we're trying to find the signed area from 0 to 2 pi. And so the hump below the x-axis has a signed area of negative 2, whereas the hump above the x-axis has a signed area of positive 2. And so the indefinite integral adds these up. And so the positive area perfectly cancels the negative area, and as a result, we get 0. And so I'm showing you this example because I want you to see that the fundamental theorem also knows about the signed area business. It's also aware of this. It takes that into account when getting the final answer. For the next example, we have to compute the definite integral from 1 to e of dx over x. So this might look a little bit weird to you, what's happening with the dx over x, but you can sort of just move the dx to the side over here, and what you'll get is 1 over x dx. So in other words, the integrand function is 1 over x, or x to the negative 1. So this definite integral represents the area under the hyperbola, or the reciprocal function, over the interval from 1 to e. And so using the fundamental theorem of calculus, we can simply find an antiderivative of the integrand, and then just evaluate that antiderivative at the endpoints. So an antiderivative of x to the negative 1, as we've discussed before, is natural log of absolute value of x. Now we have to evaluate this from 1 to e. So you just plug in e into this, and since these numbers are both positive, you can just drop the absolute value bars because the absolute value bars are redundant for positive numbers. So you get natural log of e minus natural log of 1, and natural log of e is 1, whereas natural log of 1 is just 0, and the final answer is just 1. So the signed area under the reciprocal function on the interval from 1 to e is exactly 1. And we can actually generalize and create like a formula whenever you're trying to integrate like x to the negative 1. Of course, you don't need to memorize this because whenever you see an integral like this, you can just use the fundamental theorem of calculus and write out all the steps. But let's still write the general formula down. In general, if a and b are both positive or both negative, that's important. So either you're trying to integrate on a negative interval or a positive interval. It cannot include the origin because the origin has an infinite discontinuity and the fundamental theorem of calculus only applies for continuous functions. But assuming that we're on like the positive side of the x-axis or the negative side of the x-axis, then the area under the reciprocal function is just going to be natural log of absolute value of b minus natural log of absolute value of a. And you can apply one of the properties of the logarithm, which says that if you subtract a logarithm of the same base, in this case it's log e, well then you can write as a single logarithm, base e, where you divide the arguments together. And since they're both going to be positive or both going to be negative, you don't actually need the absolute value bars. If they're both positive, then you can just drop the absolute value bar and you just get b over a. If they're both negative, then the absolute value bars can be dropped with like a minus sign, right? But then the minus signs will just cancel, and you'll get b over a. And this will be well defined because like a negative number divided by a negative number is going to be a positive number, so it will be well defined. And so what we see here is that the reciprocal function looks something like this. And if you want to find the signed area from a to b, then that value is just going to be natural log of b over a. That's what we have determined. And here's the note: if the interval where you're trying to find the signed area includes the origin, well, then the fundamental theorem of calculus cannot apply because it only applies to continuous functions on the given interval. But if you include the origin, then it's going to have this vertical asymptote, and it's going to have a discontinuity, infinite discontinuity, and so therefore the theorem doesn't apply. You cannot use this formula to calculate the value there. Instead, that will be something called like an improper integral, and we'll take a look at that much later on in the course. Next, I just want to do a few more examples, just so you get the hang of using the fundamental theorem of calculus to evaluate these definite integrals. So let's take a look at this one. We want to compute the definite integral from 1 to 27 of t plus 1 all divided by square root of t. So what we need to do is we need to find an antiderivative of this function and evaluate the antiderivative at the endpoints. However, there is no anti-differentiation rules for like quotients, right? There's no quotient rule or product rule. So as I mentioned before, the way to tackle these problems is that you have to manipulate the integrand and write it purely as a sum and difference of functions. And in this case, we can basically divide each term by square root t and square root t. And square root t is just t to the 1/2 power. And then you can use exponent properties. Like for instance, when you have t divided by t 1/2, that's just going to be t to the 1/2 power. So that's how I got the first term of the integrand. And then we also have 1 divided by t to the 1/2. And that's just going to be t to the negative 1/2. Now let's go ahead and find the antiderivative. And note that we don't actually have to write out the steps every single time, like find out the antiderivative and then plug it in. In fact, we can combine the steps into one big step. So I'm going to find the antiderivative just by using the power rule. So I add 1 to the exponent to get 3 halves, and then I have to divide by 3 halves, but dividing by 3 halves is multiplying by 2 over 3. Similarly, for this next term, I have to add 1 to the exponent, which gives me 1/2, and I have to divide by the new exponent. Dividing by a half is the same thing as multiplying by 2, and you get this antiderivative. Now we can go ahead and evaluate this antiderivative from 1 to 27. So you plug 27 into this function, and you plug 1 into this function, and subtract the outputs. So this is what happens when you plug in 27, and this is what happens when you plug in 1. Now you can use your calculator and evaluate these numbers and get the final answer as a decimal, but here I was trying to be a little bit fancy with some radical work to get the exact answer. So for instance, I know that the square root of 27 can be broken up into the square root of 9 times 3. And then you can take the radical of each, and the square root of 9 is just 3 root 3. So that means like when you see this 27 to the 1/2 power, that's basically square root of 27. It's 3 root 3. And this term over here is really the square root of 27 cubed. So just take the square root of 27, cube it, and you have to cube this answer. So you cube each number here, you get 3 cubed times, if you cube this, you can save 2 copies over here, so you get square root of 3 squared, times an extra copy of square root 3. Then over here, the square root and square cancel, and you get 3 raised to the 4th power, which is 81 times root 3. And so this means I can just replace this with 81 root 3, and I can replace the square root of 27 with 3 root 3, and that's what we've done over here. And then you just collect like terms. So these are like radicals, and you can collect their coefficients together to get 60 copies of square root 3 minus this fraction. And so there we go, that is the exact answer for the value of this definite integral. Lastly, let's take a look at one more example where we have to find the value of the definite integral from 0 to pi of absolute value of cosine x dx. So I know students get scared when they see the absolute value bar showing up. But the idea here is to somehow get rid of this absolute value bar. And to do that, we have to figure out when is this function positive and when is this function negative, because those are like the transition points where the absolute value changes sign. So let's take a look at the graph of cosine of x on 0 to pi. So we know that cosine of x looks something like this and it continues. But on the interval from 0 to pi, it's just going to be this piece. So at pi over 2 is when it transitions from positive to negative. That's when it changes sign. As a result, I want to split the interval at pi over 2. So when I integrate from 0 to pi over 2, cosine is positive. As a result, if I take the absolute value, it's redundant. It doesn't really matter. So you can just drop the absolute value bar. We're simply integrating cosine of x dx. Now on this other interval from pi over 2 to pi, cosine is giving negative output. So what's the absolute value of a negative number? Well, you can drop the absolute value as long as you multiply by a minus sign. And so on this interval, we have to integrate minus cosine x dx. And so now we can just go ahead and evaluate each definite integral here and add up the results. And I hope you noticed the property I used about the definite integral, which is that I can split it over two adjacent intervals. So we're trying to integrate over 0 to pi, but I split it up into two pieces, from 0 to pi over 2, and then from pi over 2 to pi. Right, so that's completely valid. Talked about one of those properties in the definite integral video. Now let's use the fundamental theorem of calculus. So we need to find an antiderivative of cosine, which is sine, right? Sine is what differentiates to cosine. So now I have to evaluate sine from 0 to pi over 2, and then I have to do plus the value of this definite integral. But what is the antiderivative of negative cosine? Well, what we could do is just -1. You can just factor it out of the definite integral. That's one of the properties. So that's how I got minus sign. And then what is the antiderivative of just cosine? Sine, as we discussed a few seconds ago. And so now we have to evaluate sine from pi over 2 to pi. For the first evaluation, we have sine of pi over 2, which is 1. Sine of 0 is just 0. So 1 minus 0. This just gives us 1. On this side, we have to evaluate sine of pi. Sine of pi is 0. Then we have to evaluate sine of pi over 2, which is 1. And we have to subtract the results. So we get -1. Keep in mind this has to be in brackets, right? So it's minus and then all of this in brackets. So the brackets are important. If you forget the brackets, you're going to get the wrong answer. So finally, we have 1 and then minus -1. So 1 plus 1 is 2. So notice that the answer was not 0, right? It's not like these things just canceled out. Instead, we got a positive answer, which is +2. Because we're not integrating cosine x. If you were to integrate cosine x, then yeah, they would cancel and you would get 0. But we're integrating absolute value of cosine x. What do these absolute value bars do? Well, they basically take all this negative portion and reflect it up to make it positive. So actually, the graph of absolute value of cosine x looks something like that. And so the value of this definite integral represents this area in blue that I have here. It's always above the x-axis. And in general, this is what happens. When you find the definite integral from a to b of f of x dx, you get the signed area under the curve. But if you take the absolute value, then you actually get the total area under the curve. It doesn't matter if it's positive or negative, the absolute value will end up adding basically like both pieces. That's what's happened here. And that brings us to the end of today's video, in which we covered the fundamental theorem of calculus, part 2. This is also called like the evaluation part of the fundamental theorem of calculus. And this is the key. This is the connection between the definite integral and the indefinite integral. It allows us to compute definite integrals using antiderivatives. And you can summarize the process using 2 steps. First, you have to find an antiderivative for the given function, and then just take that antiderivative and evaluate it at the limits of integration. The antiderivative evaluated at the right endpoint minus the value of the antiderivative at the left endpoint, f of b minus f of a. Now in the next video, we're going to take a look at the fundamental theorem of calculus, part 1. And so I hope you're excited to learn about that, and I hope to see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.